Assalamualaikum warahmatullahi wabarakatuh. My name is Irfan Farhan bin Zainal Akramin. Measure number AE180063. And today, we will be presenting our project, our problem-based learning on the subject of electronic communication system. First, I'm going to present about Snr Performance Parameter. What is SNR? SNR is a signal to noise power ratio. Is the ratio between the desired information or the power of a signal and the undesired signal or the power of background noise. Signal to noise ratio can be calculated using this formula, which is to get a dB, S over N is signal to noise ratio, is equals to 10 log power signal over noise power in watts. So signal to noise ratio is usually expressed in decibels. In SNR, ratio greater than 0 dB decibel or higher than 1 ratio 1 signifies more signal than noise. A higher SNR value means that the signal that is transmitted is higher than the noise generated. When the SNR value is low, the receiver will have a hard time to decipher the desired signal that is being transmitted. So that's all from me. I'm going to pass to my group member.
Assalamualaikum, my name is Nurul Iwanina binti Murni Irawan. For understanding thus, first, we need to solve the complex problem of noise impairment in communication system. Second, we need to rearrange the best amplifier position based on the given specification. Third, we need to analyze the resulting signal to noise ratio SNR characteristic. And fourth, propose a solution to reduce the noise impairment in the receiver system. So this is the flowchart of overall process to complete the task. So first, our group had a meeting to get the understanding on this project task. Next, we find some information related to main topic of this task, which is noise. After that, we divide our task evenly, and the task should be submitted 2 days before submitting final report to our lecturer. Next, we compile our task and double check our draft report before we record our presentation video. Lastly, we submit the final report and presentation video through other platform. So, for brainstorming question 1. First, we had an online discussion on understanding the question 1 through Google Meet. So to complete the part of this task, the amplifier has been arranged into 6 different positions. Then we calculate the total noise factor and signal to ratio output SNRO for each arrangement of amplifier. Lastly, we decide the best amplifier position. For question 2, first we had online discussion for understanding the question 2 through Google Meet. Next, each of our group member find any information on how do we enhance the SNRO. After that, we gather the information and we analyze it. Lastly, we pick the best way to enhance the SNRO.
Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Fabian Nazaruddin, and now I will explain to you about the question 1. Okay, this is the question. Based on the figure 1, which is the initial arrangement of cascade amplifier in the system, we need to propose a solution to produce the highest SNR output of the communication system from consistently 5-watt received signal and bandwidth of 400 MHz. We need to propose any participle solution for the SNR output based on the following condition and limitation. Okay, there are 2 condition and limitation, which is for amplifier and for chambers. For amplifiers, all the amplifier devices are portable. Amplifier 1, the gain is 4 dB or 2.119 unitless. For amplifier 2, the gain is 5 dB equal to 3.1623 unitless. And amplifier 3 is 20 unitless. Okay, for the specification of chamber, all chambers are non-portable, so we can change the sequence position for the chamber. For chamber 1, the initial temperature is 77 degrees Celsius, chamber 2, initial temperature is 300 Kelvin, and chamber 3, initial temperature is 450 Kelvin. Okay, the chamber description, for chamber 1, we can change the temperature because it is a non-controlled temperature, but for chamber 2 and chamber 3 we can change the temperature due to the range given. This chamber 2 from 25 degrees Celsius to 300 Kelvin, and chamber 3 from 22 degrees Celsius to 450 Kelvin. Okay, let's proceed to the solution. To obtaining the combination system highest SNR output, there are three methods, which is we use the initial value of the temperature of the chamber. Second, we change the amplifier position sequence, and third, we change the chamber's temperature, which is we can only change for chamber 2 and chamber 3. Okay, this is for method which is initial value. We use initial value temperature by taking the initial value temperature. Okay, given SI is 5 watt and bandwidth is 400 MHz. Okay, in order to find the SNR input, it is equal to SI over NI. So we need to find NI first because SI is given from the question. NI equal to KTB, which is K equals one constant, T is absolute temperature, sorry, B is the bandwidth. So all the parameters have been given in the equation. NI equal to 1.7 multiplied by 10 to the power of negative 12 watt. Okay, now we can calculate the SNR input, which is SI over NI, and we get the SNR input is 2.9409 multiplied by 10 to the power of 12 unitless. Okay, next we find the noise factor of each amplifier and chamber. So the noise factor formula is equal to 1 plus the chamber temperature divided by absolute temperature. We get for the chamber 1 equal to 2.1364, chamber 2 equal to 1.9740, and noise factor for chamber 3 is equal to 2.4610. Okay, after get all the noise factor for each chamber, we need to calculate the total noise factor, which is equal to F1, the noise factor for chamber 1 plus noise factor for chamber 2 minus 1 divided by the amplifier 1, and plus with the noise factor for chamber 3 minus 1 divided by the multiplication of amplifier 1 and amplifier 2. We get the total noise factor for the first method is 2.7081. Okay, then we can calculate the SNR output, which is SNR input equal divided by total noise factor. We get the SNR output for first method is 1.0861 multiplied by 10 to the power of 12 unitless. Okay, next we move to the second method, which is we change the amplifier position sequence. By changing the amplifier position sequence here, we can get the total noise factor, and then we can calculate the SNR output for each sequence. As we can see, the SNR output, the highest SNR output is the last one, which is we put the sequence from amplifier 3 to amplifier 2, and last for the amplifier 1. We get the SNR output equal to 1.3318 multiplied by 10 to the power of 12 unitless. Okay, next we move to the third method, which is we change the chamber's temperature. Okay, by taking the minimum temperature, we can calculate the noise factor. For chamber 1, the noise factor is the same with the initial temperature, but for the chamber 2 and chamber 3, we use the minimum range of the temperature for each chamber, which is 25 and 22. We put in the formula, and we get the for noise factor for chamber 2 is 1.9675, chamber 3 1.9578. Okay, next we can find the total noise factor equal to 2.6421, and then SNR output, which is equal to 1.1131 multiplied by 10 to the power of 12 unitless. Okay, the decision on the best possible output of or in other words, decision method for the to get the highest SNR output. Okay, we can, after we analyze all the result, we find that in method 2 is the highest SNR output, which is the sequence of 3 to 1, which is with 1.3321. 218 multiplied by 10 to the power f12. So from this method 2, which is a method change amplifier the audio sequence, it is shown that the factor that affect the signal to noise ratio output SNRO is the total noise factor. From our sequence, the sequence start with amplifier 3 to amplifier 2 and the last to amplifier 1 has the lowest total noise factor. If we compare all of that total noise factor, this is because regarding for the formula of SNR output, the noise factor is inversely proportional to the SNR output. Okay, next, to further strengthen the theory is by comparing the SNR output for method 1 and for method 3. Okay, the SNR output for method 1, which is 1.0861 multiplied by 10 to the power of 12 meters, is lowest than the SNR output for method 3, which is 1.1131 multiplied by the 10 to the power of 12 meters. While for the total noise factor for method 1, which is 2.7081, is the high than the total noise factor for method 3, which is 2.6421. Therefore, it can be concluded that the lower the total noise factor, the higher the SNR output. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Snr Performance. My metric number is AE180105. So in this video, I will explain about the answers for question 2 for this task, which is the question is without considering the mentioned condition or also limitation, what could we propose to further and in order to enhance the output for signal noise ratio or SNR. Okay, from this question, the task is us to discuss and also elaborate. The first method that we suggest is by reducing bandwidth of the receiver, as the noise can be propagated across all frequencies. It turns out that the higher the receiver bandwidth, the higher the level of noise. Noise power can be calculated as in the formula given. Okay, N equals to KTB, where K is represented as Boltzmann constants, T equals to environmental temperature in Kelvin, D is bandwidth in Hertz. Okay, from the equation shown, the noise power is directly proportional to the Boltzmann constant, temperature, environmental, and also bandwidth. So when the bandwidth is reduced, the noise power also reduced. This is related to the signal noise ratio formula, whereas signal noise ratio is directly proportional to the signal power over noise power. So it can be concluded that the value of noise power the value of the noise power decrease, so the produced SNR will opposite, which is increase. Okay, the second is for the modulation. It is better if we use the signal sideband or SSB as modulation because its spectrum space is only half of amplitude modulation AM and double sideband DSB or in short form DSB. This will allow more signal to be transmitted in the same frequency range where there will be less interference between the signal. The laser size bandwidth, of size of the bandwidth will affect the noise reduction and also enhance the SNR output. So from this explanation, we know that at the end it will also, by using this method, at the end it will give the best result for the output, which is enhance the output. That's all from me in this video. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Patricia Balkis binti Jensen Hadi with metric number AE180040. And now I will continue on question 2, gathering the information to decide the best solution to enhance the SNR output. Next is local oscillator and mixing. This is used to move the input signal to another frequency band. Local oscillator and mixing is very useful to remove most of the low frequency noise interference associated with 50 and 60 Hz and create a final output signal with an exceptionally low noise signal. Mixer here is usually reserved if we have a particular target frequency that we are interested in. When two frequencies are combined, we get these two frequencies, for example, 100.5 MHz and 89.8 MHz. But we not just only get these two frequency, but we also get their sum and different derivative frequency, which is 10.7 MHz and 190.3 MHz. The radio industry has standardized a specific filter frequency for both FM and AM radio, which happens to be 10.7 MHz for FM and 444 kHz for AM. So this example is referring to FM radio frequency. Okay. So here the filter will eliminate everything except the range between two frequency, allowing only that frequency to pass. Okay, next we can use parallel amplifier. This technique can improve as our SNR output, lower voltage noise density, and output offset error is reduced. If we are referring to our group assignment, which is limitation and condition, there are three amplifiers. So in this situation, we use three amplifiers in parallel. The noise power of the amplifier is reduced by 3, and the voltage noise density with respect to input is reduced by 3. This we can prove it by using this formula. First, we have to get an I gain and the N amplifier. Okay, and then we use SNR calculation for 3 amplifier, and we substitute all the value, and here is our final answer, which is 8.6505 times 10 power of 24. So it is example for calculation when we using parallel amplifier. So the decision of the best solution that we are choose is paralleling amplifiers technique. This is because this technique can improve SNR, which is our main target, lower voltage noise density, output offset error is reduced. If we can see, the SNR output that we get from the calculation is 8.6505 10 power of 24, which is when we compare to all the original calculation on question 1, this SNR output is highest compared to others. So we will choose amplifier technique as our decision. Thank you. That's all from me.